We trust the world around us, solid, predictable, and governed by rules we understand. The chair beneath you, the floor, the rising sun, these are the certainties of our daily lives. But what if this solidity is just an illusion? Beneath the surface, reality is built on a foundation of chaos and strangeness, the world of quantum mechanics. Zoom in past atoms, and the rules of the classical world vanish. Here, subatomic particles, electrons, quarks, photons, don't behave like tiny billiard balls. Instead, they exist as waves of probability, not in one place, but in a haze of potential locations. An electron isn't here or there, it's everywhere it could possibly be, until measured. The idea of a definite position becomes meaningless. Think of a cloud of smoke. You can't point to a single spot and say, the smoke is here. A subatomic particle is a cloud of potential, a wave of existence spread across space. Only when we interact with it does this cloud collapse into a single, definite point. The solid world we experience is born from this constant dance between uncertainty and certainty. Our reality is forged from pure potential, flickering between what could be and what is. Welcome to the quantum world, where nothing is as it seems. The quantum world's strangeness is captured by wave-particle duality. Every fundamental particle, like photons and electrons, has a split personality. Sometimes it acts like a tiny, localized particle. Other times, it behaves like a wave, spreading out and interfering with itself. It's not one or the other, it's both, simultaneously. This isn't a metaphor, it's the physical reality of the subatomic world. Imagine being both at home and in the park at the same time. That's superposition. For an electron, this duality is natural. It exists as a wave of potential, able to be found anywhere along its front. This isn't a flaw in our understanding. It's the fundamental truth of matter. The universe isn't built from simple, solid bricks, but from entities that are fluid and mysterious. Their behavior changes depending on how we interact with them. Wave-particle duality isn't just a curiosity. It's why atoms are stable and the sun shines. It's the core principle underpinning reality itself. The double-slit experiment reveals quantum reality's true weirdness. Fire electrons one by one at a barrier with two slits, and watch the pattern on a screen behind. If electrons were just particles, we'd see two bands. But instead, we see an interference pattern, stripes of light and dark, just like waves. Even when sent one at a time, each electron seems to pass through both slits and interfere with itself. It's as if each particle explores all possible paths at once. The electron leaves as a particle, becomes a wave to pass through the slits, then lands as a particle again. This experiment forces us to confront quantum mechanics' core mystery. A single particle can be in multiple places and take multiple paths at once. The double-slit experiment has been repeated with electrons, photons, even molecules. Always the same result. Reality at this level isn't fixed. It's a shimmering wave of potential. The quantum world is a collection of all possible stories happening together. Our everyday logic simply doesn't apply. The double-slit experiment gets even stranger when we try to observe which slit the electron passes through. Place a detector at the slits, and the interference pattern vanishes, replaced by two simple bands. The act of measurement forces the electron to choose a path, collapsing its wave of possibilities into a single outcome. This is the observer effect. Reality changes depending on whether we're watching. Before observation, the electron exists in a superposition, passing through both slits at once. Measurement collapses this cloud of possibilities into one reality. The universe seems to wait for an observer to decide its fate. What counts as observation? Any interaction that extracts information is enough to collapse the wave function. The implication is staggering. The quantum world isn't a pre-existing reality we uncover, but one we help create through measurement. We're not just spectators, we're participants, shaping the outcome. At the quantum level, reality is participatory. Not everyone accepted quantum strangeness. Einstein famously objected, "God does not play dice." He believed reality must be definite, with hidden variables we hadn't found. But experiments proved him wrong. There are no hidden variables, and quantum uncertainty is real. A particle's properties don't exist in a definite state until measured. This led to mind-bending ideas like the many-worlds interpretation. Every quantum choice splits the universe into parallel realities. In one, the electron goes left. In another, right. Every possibility plays out in its own cosmos. Quantum entanglement, what Einstein called spooky action at a distance, links particles across the universe, so measuring one instantly affects the other. It seems to defy the speed of light, pushing the boundaries of our understanding. These ideas remind us, the solid world we know is just the surface of a much deeper, stranger reality. The quantum world is endlessly mysterious and endlessly fascinating.